All right, welcome to calculus. We are going to start this unit and 1.1 with a warm intro into limits. And before we dive in, we will at least explore a little bit the first type of problem. But on this slide, you'll see two different important topics for the year, essentially. Um, when you think about calculus, these are the two things that you're going to sort of retain. The first is what we call the tangent line problem, and that is pretty much just finding the slope of a tangent line. We'll talk a little bit more about that. The second one is more of the B component part of calculus, and that's going to be finding the area under any curve, any type of curve, any graph, over a closed interval. So both of these things can be found using limits. Let's touch a little bit more on the tangent line problem. I'm going to use Desmos for this. So for the tangent line problem, what that's saying is a very useful tool in calculus is finding the slope of a tangent line at a specific point. So let's say, for example, we wanted to find, what's that point? 0.62. We wanted to find the slope of the tangent line when x is 0.62. I want to find the tangent, and remember back in geometry, tangent lines are lines that hit either a graph or a circle at exactly one point, whereas a secant line hits it in more than one point. So what we do is we are going to use this secant line, which is in red here, and we're going to use that to approximate what the tangent line slope will be when x is 0.62. And you'll see over to the left, I'm going to highlight it, that, and you don't have to worry about any of the mess just yet, but you'll see that the slope is 0.258. So that's a pretty poor approximation, right? But what happens if we let the difference in the distance between these 2 points get smaller and smaller so that it approaches zero? Now we'll see that we're getting closer and closer to the tangent line. But when those two overlap, you'll see over on the left, it says undefined because 2 points determine a line, right? So what we can do instead is use that secant line, and we're going to let the distance between those 2 points approach zero. We're going to do that using limits. And so on the left, you'll see 1.102 is what our decent approximation is. Okay, so what is a limit even? So here you'll see at the top one definition, and I will let you read that and pause it if you just want to go and sort of internalize that. And I'm going to paraphrase that. So pretty much what we're doing, if we're thinking about graphs, because I like to use visuals for this, a limit is a y value, a height that a graph is trying to approach, and whether or not it actually gets there is irrelevant. So let's give a quick example. So I'm going to give two. So let's say this is 4 and this is 9. That's my x. This is f of x. And then over here, in this color, three, 7. So by definition, a limit is the y value, the height that your graph is intending to approach at a specific x. And then the disclaimer is whether or not it gets there is irrelevant. So let's look at the f of x graph, and I'll call this one g. So if we were looking at, I'll go a different color. If we're looking at the height that this graph, f of x, is trying to reach as we get closer and closer to x equals 4, I'm going to do two things. I'm going to look at the y values of the x's near 4 from both sides. I'm going to look at the y values of the x's near 4, meaning I don't care what it is at 4, but as I'm getting closer and closer to 4 from this side, what are those y values trying to reach? And it looks like they're trying to get closer and closer to 9, right? And then I'm going to do the same thing from the other side. What are those y values trying to reach? And same, right? They're trying to reach 9. So I would say that limit for this f of x is 9. And now, if I look at the g of x, I'm going to do the same thing if I'm trying to find the limit as I'm getting closer and closer to 3, as my x value is approaching 3. Now let's see what's going on here, and it looks like those y values on this direction, those values are trying to approach 7. And then from this direction, it's the same thing. Now I'm going to add a little something here. Well, that's still legit. So now I hope you would say, if we said, well, what's g of 3? You would tell me that g of 3 is 12, because it is, right? There's that point that's establishing that that's the y value. But my limit as my x approaches 3 for g of x is 7, because the values near 3 are trying to approach 7. So you'll see that that bottom statement is just saying, and we're not going to do this in this section, but we will do it in this chapter, that we are going to be using limits to find slopes, to find approximations of slopes of tangent lines by using the secant lines. We're going to take that limit and we're going to let the distance between those 2 points approach 0. More to come on that one. So this is pretty much just your definition, the definition that we are going to use for our purposes of calculus with limits. And it's a little wordy, but it's what we've been saying before. We are looking at, if we say that limit, and I'm going to read how that's read. It's the limit as x approaches a of f of x equals L. And that's true if we are looking at values, x values, near a, not at a, but near a. And that's if they both approach from both sides, that number L, then that's what the limit would be. And that bottom preface is saying, we don't care what happens at A. It could be whatever it wants to be at A. We're looking at the values near A. We're going to do several examples of this. So I'm going to use my graphing calculator for this one. And I don't have an emulator, so I'm going to actually have to show you my calc. So this is asking us to find numerical evidence to make a conjecture about the limit for this function as x approaches 1. So numerical evidence just means, let's look at the table. Let's look at the table of values near x equals 1, near x equals 1, to figure out what that limit would be. So x minus 1 over root x minus 1. Here we go. So I'm going to go to, so here is my graphing calculator, and in my y equals, I'm going to plug in that function. And so I like to go to alpha y equals, and you'll see n over d, and that just gives me that nice little fraction. And then x minus 1, and then root x, and then get out of the radical, minus 1. And remember, we wanted to look at the, so that's my function, we wanted to look at the limit as x approaches 1, right? So then I'm going to go to my table set, because I'm going to use my table. And since I want to see what's going on at 1, I want to start my table at 1, and then And then what? The delta table is the increments, right? What do we want our increments to be? The more exact we can be, the better. So the closer those values are to 1, that's going to be in our favor. So how about 0.001? I like that. Now I went to second graph to see the table. And now you'll see, and this is useful, I don't care what happens at 1. And you'll see the y value at 1 is nope, undefined, right? We have an error. But if we're looking at the values near 1, from this direction, we're getting 1.999, 1.9995. And if we made our delta table even smaller, what do you think those values are going to approach? 2, right? And then from this direction, it's the same idea, except these are slightly larger than 2. But the closer we get to 1, the more those y values will be closer and closer to 2. So what? So now we would say, for this example, that limit is approaching 2. All right. Now we're taking on what we refer to as one-sided limits. So we haven't been using the notation, and so we're going to introduce this vocabulary now. We have one-sided limits, and what's really important about one-sided limits is that if I'm looking, like we did at x approaches 1, I need to look at the values that are approaching 1 from both sides. We're going to have a left-hand limit. We're going to have a right-hand limit. So let's look at this notation. So if we go to the left column, that's our left-hand limit. And you'll notice this notation, and I'm going to read it. It's the limit as x approaches a, and you see that superscript with the negative. That means x approaches a from the left. That tells us that we're looking at the x values that are slightly smaller than a. So if we were looking at, for example, the limit as x approaches 3 from the left, I'm going to look at values like 2.9, 2.99, values that are close to 3 but just a little bit smaller. And then the right is the same thing, pretty much, right? And now I'm thinking the limit as x approaches a from the right, and you'll see that that's a plus sign, right? That's a plus sign. So if I'm looking at the limit as x approaches 3 from the right, I'm going to look at values like 3.01, 3.001, and on and on. Now, this is important. In order for a limit to exist, the limit as my x is approaching a from the left has to be equal to the limit as my x approaches a from the right. If those two values don't approach the same thing, we say that the limit does not exist, and we abbreviate it by DNE. I hope that makes sense. Okay, so this one's a really good example. And if you have time, I might just reflect on this before I plug it into my graphing calculator, or maybe I'll use Desmos just so I don't have to stand back up again, so that we can see what this graph looks like. It's a super special graph in that this equation is used very frequently because of the nature and the way it looks. So for this question, they're asking us to find the limit as x approaches 0 from the left and as x approaches 0 from the right. So we can do this one of two ways, people. We could plug in values that are close to 0, but slightly smaller, and then we can do the same thing as we're approaching 0 from the right. We can also just use the graph to aid us in this. So what I'm going to do is, I'm going to go to Desmos, and I'm going to type in the absolute value, and you can do this on your graphing calculator, of x divided by x. And if you see it right here, it's red. It's going to change the color, make it a little clearer. Blue. Yeah, still not very clear. I'm going to write it. So that looks like this. Because I want it to be super clear what's happening. That's my x, that's my y. So this is the graph of the absolute value of x over x. And our question was, what is the limit as my x approaches 0 from the left, and what's the limit as x approaches 0 from the right? All right, and I'll just do the notation. So I'm hoping that if you're looking at the limit as x approaches 0 from the left, you've got the right idea. We're looking at those y values as I'm getting closer and closer to 0 from this direction, and what are the y's trying to reach? Right, -1. And then, if we're looking at the second, as x approaches 0 from the right, it's the same idea, except from that direction, they're approaching 1. So what's our conclusion for the limit as x approaches 0 for this function? We would say that limit does not exist because our left-hand limit is not equal to our right-hand limit. All right, so I'm going to do let's do the first column together for this example, and then I'll have you do the second. So if I looked at the limit as x approaches 2 from the left, if I looked here, I'm looking at those values that are close to 2, as I'm getting closer and closer to 2 from the left. And what do those y values look to be approaching? 3. So we would say that the limit as x approaches 2 from the left is 3. Now, what do you think is going to happen as I'm approaching 2 from the right? Now I'm looking at values like 2.1, 2.01. And as I'm approaching from that direction, that looks like they're approaching 1, which gives me here, because that left and right-hand limit are not the same, that's a DNE.